This video is a part of series of videos about the design of curved beams. We have discussed the analysis and design of vertically curved beams that are mainly used in arc bridges where the load is in the plane of curvature. You can find the video at the top right corner or in the link in the description below. This video discusses the design of horizontally curved members in torsion. Horizontally curved members are loaded perpendicular to the plane of curvature. We have discussed the analysis of such members as well as spiral helical members in another video. You can find the video at the top right corner or in the description below. Horizontally curved members are often used as curved crane rails. Because both torsion and flexure are present in curved beams, the second-order effects and interaction equations are required to verify the member strength. In all cases, the torsional strength is calculated for an equivalent straight member based on the developed length between torsional restraints LDB and properly accounting for any warping restraints. AISC Design Guide 9 can be used to calculate the elastic torsional strength of an equivalent straight member. Hence, this method is called the elastic method. Because the torsion diagram for curved beams are typically nonlinear, conservative assumptions are usually required to accommodate the design charts in Appendix B of the design guide. The simplest loading case with a uniform moment over the unbraced length results in a uniformly distributed torsion. For this loading condition, the torsional functions can be determined with case 4 or case 7 depending on the warping boundary conditions at the supports. For simply supported beams subjected to uniformly distributed loads, the maximum value of mx within the span can be used as a conservative estimate of the uniform torsion per unit length. Using this simplification with case 4 for a beam with free warping at the boundaries results in an overestimate of torsional rotations by 23%. For composite I-shaped beams, the torsional properties are based on the idealized transformed section shown. The torsional constant, warping constant, normalized warping function for the slab, the normalized warping function for the steel section, the warping statical moment for the slab, and the warping statical moment for the steel section, as well as the shear center location, are then evaluated as such. When the torsional function values are extracted from the graphs in Appendix B of Design Guide 9, these section properties can be used to evaluate the pure torsional shear stresses, the shear stresses due to warping, and the normal stresses due to warping. Another method is the isolated flange method. For I-shaped members, the warping strength can be approximated by isolating the flanges and treating them as independent rectangular beams loaded in the horizontal plane by a distributed radial force per unit length calculated with this equation. The radial force is applied toward the center of curvature at the tension flange and away from the center of curvature at the compression flange as shown. For the simple loading case with a uniform moment over the unbraced length, the bending moment caused by the radial forces for a laterally braced horizontally curved beam against warping looks like this. The moment diagram for the equivalent straight beam isolated flange is based on a fixed uniformly loaded beam. The basic steps for the isolated flange method are: construct the primary moment diagram for the equivalent straight beam segment between points of torsional restraint LDB. Then, convert the warping boundary conditions to the appropriate flexural boundary conditions for the isolated flange. Afterwards, using the primary moment diagram and this equation, calculate the distributed radial force per unit length FFC to be applied to the isolated flange. Then finally, construct the moment diagram for the isolated flange. The bending strength about the axis of bending for the flange can then be calculated with this equation, where ZF is the plastic modulus of the flange. The maximum moment would then be compared to the calculated strength and combined actions of flexure and torsion, including second-order effects, should be evaluated. After the required flexural and torsional moments are determined, the available member strength is calculated either by combining the stresses or by combining the load ratios in an interaction equation. In either case, second-order effects must be considered. Second-order torsional moments and rotations can be calculated either by using a rigorous second-order analysis or by amplifying the results of a first-order analysis. For open sections subjected to both torsion and strong axis flexure, the second-order torsional rotation and the second-order torsional moment are amplified using the factor BO. The moments are used when using the isolated flange method, and the stresses are used when using the elastic method along with Design Guide 9. Round, square, and rectangular hollow section members can be designed according to AISC specification section H 3.2 for combined flexure, shear, and torsion. For evaluation using stresses, the bottom equation can be used. For hollow sections, either the elastic method or the following equations can be used to calculate the torsional strength. Large vertical, horizontal, and torsional deformations at ultimate strength often result in designs based on serviceability rather than strength. A reasonable limit on the maximum angle of rotation will ensure non-structural elements are not damaged by excessive rotations. There are no formal limits in building codes. Therefore, judgment should be used to define the appropriate deflection and rotation limits based on the type of building elements supported by the beam. Additional considerations such as floor vibrations may result in other serviceability performance criteria. In the serviceability evaluation, the maximum normal stress in the member should be limited to the first yield stress. Alternatively, for I-shaped members in the inelastic range, the torsional rotation can be estimated with this equation. The value of alpha t can be estimated with the equation on the left for the isolated flange method and the equation on the right for the elastic method. For closed shapes, a strength evaluation according to these equations previously mentioned will ensure nominally elastic behavior, and the elastic deformations can be used to evaluate serviceability limits. When curved round hollow section members are subjected to out-of-plane flexure, the flexural strength and stiffness can be reduced by ovalization of the cross-section. The deformed shape caused by the out-of-plane bending, where the major axis of the ovalized shape is skewed at an angle of approximately 35 to 45 degrees from the axis of flexure, is shown. The flexural section properties are functions of the flexibility characteristic C sub r, which is defined by this equation. Because significant nonlinear ovalization can occur when the member is loaded beyond the effective yield moment MYO, limiting the nominal flexural strength of these members to MYO may be appropriate. For out-of-plane bending, the effective moment of inertia is identical to that of in-plane bending. When fatigue or local strength is an issue, the circumferential stresses can be calculated with a multiplier on the longitudinal flexural stress according to this equation. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.